The table below shows the structures of three isomers with the molecular formula C5H10O. 1, 2 and 3. So complete the table by naming isomer number 3. So isomer number 3 is a ketone. So 1, 2, 3, 4, 5. So it will be pentan 2 own. So we do need the number here because of course it could be on carbon number 3. State the type of structural isomerism shown by these. So we've got functional group isomerism because this is an aldehyde and this is an alkene with an alcohol on it. So this is functional group isomerism. And then part C, the compound Z-pent-3-ene-2-ol is a stereoisomer of E. Draw the structure of, so pent-3-ene-2-ol. So let me start with a double bond like this, and kind of doesn't matter which way I number, so I'm going to number from right to left. So this will be carbon number 3, that will be 4. So if I do carbon number 2 here, so CH, that's going to have an OH on because I've got a 2-ol, and then I'm going to have a CH3 over here. So this is going to be a hydrogen over here. So, and then I've got 1, 2, 3, 4, 5, and Z means they're on the same side. So you can either do CH3 here like that, or you could write it as H3C. Just making sure that that bond points to the carbon. And then we've got the hydrogen over here. Part 2, the feature of a double bond that causes these two compounds to be stereoisomers. So restricted rotation. Around the carbon-carbon double bond. And yeah, that's it for that mark. Part D, a chemical test can be used to separate samples of isomer 2 and isomer 3. Identify a suitable reagent and what you would observe with 2 or 3. So 2 and 3, so this is an aldehyde. And down here we have a ketone. So aldehydes can be oxidized further, so you can take your pick from Tollens reagent or Fehling solution or acidified potassium dichromate. Any one of those three will do, but I'm just going to pick one of them to do. So I'm going to pick Tollens reagent. I will talk through the results in a moment of the others. With 2, that's the aldehyde, so I'll get a silver mirror or a silver precipitate, and no observable change. Now, if you were to use Fehling solution, you would see a brick red precipitate here, and again, no observable change with isomer 3. And if you were to use acidified potassium dichromate, you would see orange to green over here, and again, no observable change down here. Okay, so those are your other options. Part E, the following is an infrared spectrum of one of the isomers, 1, 2, or 3. Deduce which of the isomers 1, 2, or 3 would give you this. You may find it helpful to refer to the data sheet. So this here is screaming at me that it is an OH. And if I go back to my isomers, there's only one of those with an OH, and that is isomer 1. If you check it on the data sheet, you'll see that it's the OH absorption in an alcohol. So that means this is going to be isomer 1. And then identify 2 features in the infrared spectra that support your deductions. In each case, identify the functional groups that are responsible. So the oxygen-hydrogen bonds, that's one that I've just been talking about. So on your data sheet, you will see that we have a peak. So you have to quote the data sheet. We have a peak between 3230 to 3550. Okay, So there's one of them. There are two others that you could go to. So another obvious one is that in isomer 1 there is no carbon-oxygen double bond or no carbonyl peak, which we would find, again, you've got to quote the data sheet, so between 1680 to 1750. And there is a third as well for isomer 1. Again, if we go back to isomer 1, you can see that isomer 1 has the carbon-carbon double bond. So you could talk for a possible third one here, that we have a carbon-carbon double bond between 1620 to 1680. So there's a kind of third option there, that we have a carbon-carbon double bond peak between 1620 to 1680. Okay, so any two of those three would get you those marks.